Okay, so as we've seen in the last section, we arrived at a scenario where we know the charge at any time as we're discharging is given by the total charge, or the full charge, Q naught, times by E to the minus T over RC. And we said that this is true for any value that is undergoing exponential decay during the discharge cycle. So it's true that the current at any stage will be given by the initial current times E to the minus T over RC, RC, and it's also true that the potential difference across the plates will undergo the same form of decay. And of course, therefore, we've got these three equations that are all equal. But this is only for discharge, and this is the key point about this. All this applies to discharge. But let's think now what's happening if we are charging up a capacitor. Well, it stands to reason, I think you'll be able to appreciate that it stands to reason that if we're charging up a capacitor, then it's going to look slightly different. If we think about a cell like that, a switch like this, and our capacitor, let's say a capacitor's there, and you first close the switch, ka-ching, current starts to jump onto the capacitor. Now there's no, in this immediate case, in this scenario, there's no resistance in the circuit apart from the internal resistance of the cell. So as we first close the switch, there's nothing to stop this current flying, these charges flying onto this capacitor. So if we were to think about the, let's just say, let's stick with charge. If you think about the start, it's going to be flying on there. It's going to be a big current. Remember the current over time graph, charge over time is the current. So if there's a large current as it's flying on, we're going to have a steep gradient at the start. And then as it builds up over time, this is going to diminish. And so if we had a graph of charge versus time in the first instance, that's Q naught, i.e. being the, Q naught being fully charged, okay, and before when we were charging it, Q naught's fully charged. Just doing this, you can see basically it's the inverse scenario, it's the opposite situation. Now the maths of this is pretty simple. If it's discharging, we say it is Q equals Q naught, i.e. the full charge, E to the minus T over RC. And if it's charging, it's Q at any time equals Q naught times by 1 minus E to the minus T over RC. That's all there is to that. Now, this of course is the same, as I said before, there's three versions. This is the Q, there's the I, and there's the V, and it's the same for both. So this shape graph is the charging cycle. This is all for charging. I should actually get rid of this. This is all for charging, and this is for discharging. Now I might do a separate video of the maths of how you get to this from this, but it's not particularly complicated, but takes a little bit of time, and it's not necessarily for the syllabus. What is important is that if you were to get a set of data and look at a graph like this, well, you want to know the significance of the time constant. Remember, the time constant, RC, is how long it takes for, in a discharging cycle, constant, so I can't talk and spell. Remember, it's the time it takes in a discharging cycle for this to fall to 37%, or 0.37 times by Q naught. But of course, if you think about it, if this is RC here on this graph, well, this is going to be 1 minus, so when you're charging, it'll be the time for it to get to 0.63 of Q naught. Okay, so there's two key numbers, yeah, and you can basically just work this out from the graph. It's very straightforward. The two key numbers. If it's discharging, it's basically the time, I'm going to say time to reach or to fall to 37% when you're discharging, or time to reach to rise to 63% of full. Now this is of course if you're discharging, this situation here, and this is of course if you're charging, this situation right here. So I will make another separate video of how you get to that, because it's only about a 2-minute job, and I'll shove that in there. But that is the two equations that you're going to need to do this, and this is basically the maths of charging and discharge charging. That's really all we need for this bit.